thank you for those of you who joined us again this month for another iteration of our Oregon Beaches Forever webinar series. I'm very excited to welcome Haley Bond to talk about all things cobble berms, but first I will tell you a little bit about Surfrider and the Oregon Beaches Forever campaign. I'm Kaya Hazard. I am Surfrider's Oregon Field Manager. Surfrider is a nonprofit organization, and our chapters in Oregon work to protect our ocean waves and beaches through grassroots organizing and advocacy. So we work on issues like plastic pollution, water quality, beach access, and making our coastlines and coastal communities more resilient. So to that end, Surfrider has teamed up with Oregon Shores to launch our Oregon Beaches Forever campaign. Through this campaign, we're taking a holistic approach to protecting our beaches. We not only oppose harmful shoreline armoring along our coasts on individual and beach-wide scales, as is the case with Beverly Beach, but we're also working on the implementation of nature-based erosion solution model projects like Adicola Creek and policies that promote beach preservation and climate adaptation so that we can move away from hardened shorelines. We're also advocating for local level climate adaptation and improved shoreline management at the city and county level. For example, we worked with Clatsop County to update their comprehensive plan that was just adopted last week and has some really great language in there protecting our public beaches. And last but not least, we'll be working with state agencies on their rulemaking processes to update and improve existing regulations for shoreline armoring, permitting, and access to and along the shore. So if you would like to learn more about this campaign and stay up to date with upcoming events like this one, you can find more information on both Surfrider and Oregon Shores websites at the link, which I will drop in the chat shortly. I'm just going to plug here. We'll have 2 more webinars to finish out the year. On November 5th, we will welcome Steve Dundas, and then on December 1st, we will welcome Rhiannon Bezorer to talk about the Oregon King Tides project. And we'll also have 2 in-person events. On November 13th, we'll be in Newport talking about ODOT's plans to armor Beverly Beach. And on December 6th, we'll be doing a King Tide watch party in Cannon Beach. So with that, I will turn it over to Rhiannon to talk a little bit more about King Tides.
Thanks, Kaya. I just wanted to give a quick plug and reminder for everybody that King Tide season is coming up very quickly. So these are the extreme tides that we see every winter due to the alignment of the planets and the moon and the sun. And the first round will be November 5th. Then the December 4th to the 6th and January 1st to the 4th. And every year, Oregon King Tides Project asks that participants submit their photos to help document the different impacts from these high tides, including coastal erosion, flooding, other types of impacts that you can see in bays and estuaries. And you can submit all of those photos to OregonKingTides.net, and I'll put that in the chat as well. And it also has a lot of great information on there about different events, as well as more information about King Tides themselves. So thanks.
Thanks, Rhiannon. Thanks, Kaya. I'm so excited for King Tide season. Hi, all. My name is Mandy Watson. I'm the Coastal Conservation Manager for Oregon Shores. Oregon Shores is a nonprofit that focuses on ocean and coastal issues here in the state of Oregon. And our vision is a healthy and resilient Oregon coast where nature and people thrive together. And we do this by educating and empowering people to protect coastal ecosystems as well as coastal communities. We do this work through kind of 2 main avenues, policy advocacy and education and outreach. We're probably most widely known for our Coast Watch program, where people adopt a mile of the coast to monitor and steward record changes and contribute to a statewide citizen science project. We also have our policy advocacy team, and this spans everything from influencing land use and shoreline planning decisions with our Oregon Beaches Forever team, as Kai mentioned, to lobbying for coastal habitat protections at the state legislature, to preventing bad development on Oregon's estuaries, beaches, and dunes. And for more information, you could visit our website to get more involved. And today we're super lucky to have Haley Bond with us. Haley is a doctoral student in coastal ocean engineering at Oregon State University. She earned a Bachelor of Science in Civil Engineering from Cal Poly San Luis Obispo's, Go Mustangs, and her master's in Coastal and Ocean Engineering at Oregon State University, where her research focused on the formation of scarps on dunes during extreme events. After earning her master's, she worked with the Oregon's Department of Land Conservation and Development as a Natural Resource Policy Fellow, where she created Oregon's Erosion Control Guidebook. Haley's PhD research is focused on improving engineering guidance for dynamic cobble berm revetments through field and laboratory work. So thanks so much for being here with us today, Haley. Feel free to take it away.
Thank you for having me. I'm going to share my screen really quick. Okay, thank you. So today I'm going to be talking about dynamic cobble berm revetments and how we are developing engineering guidance for the Pacific Northwest and beyond. First, an introduction. My name is Haley. I'm a PhD student at Oregon State University. I'm actually in my final year of my PhD. I'm supervised by Megan Wengrove, who has also been a part of this seminar series. And my whole PhD is focused on dynamic revetments. And if you've never heard that term before, don't worry, we'll get there. My main goal of my PhD is to do science that supports engineering guidance for dynamic revetments. And so the objective of my presentation is to try and show an example of the way that science can make its way into engineering guidance. So first, I want to start by talking about natural and nature-based features. They're known by many names, including living shorelines, engineering with nature, nature-based solutions, many other kinds of things. Usually these structures aim to solve some type of coastal problem, erosion, flooding, or what have you. And they try to use natural processes and natural materials to solve this coastal problem. So you can see in examples around here, there are oyster bags and planted grasses and mangroves, all sorts of things. And natural and nature-based features, the idea of them is that they're supposed to support existing ecosystems. Yeah, planting grass that already exists in the area, that type of thing. Natural nature-based features have a lot of pros. First of all, they fit
Sorry,
in with the.
Haley,
Oh
can I
yeah,
cut in for a second?
yeah.
I am wondering if they can't see your slides. We
That
got
is possible.
a message in the chat. Oh, no,
I
someone can see them. Okay.
okay.
Can everyone
Well,
chime
I'll
in and
share
maybe,
again.
okay, can everyone see that? Yes.
Yeah,
Okay,
we're good.
sorry, we're good.
Okay, all good. Okay, some pros of natural and nature-based features. First of all, they fit in with the local environment and the local ecosystem. They might help an existing natural system to function again. So if you have an area that is no longer functioning as it should because of like extreme erosion or a bad flood or something like that, you can help the natural system a little bit to make it function again. Another interesting thing about natural and nature-based features is that failure isn't always black and white. For example, if you have traditional riprap where you pile rocks up to prevent against coastal erosion, if one of those rocks moves, that's considered failure. But if you have a natural and nature-based feature, if you have some plants that die off, if you have a bad storm with some erosion, that's not necessarily a failure because the system has like inherent resilience that it might be able to kind of bounce back. Natural and nature-based features can be cheaper. And one other interesting thing that I've been talking with collaborators about is that we think that natural and nature-based features can kind of help to enhance community understanding of natural processes because when you put in a natural and nature-based feature, it's different, people are interested, they ask questions, and sometimes scientists come in and give seminars like these, where the public gets to learn a lot more about what the forcing conditions and the environment is doing, which kind of helps everybody understand a little bit more about what's going on the coast. And lastly, and maybe some people would say most importantly, if you use a natural and nature-based feature instead of traditional riprap, it can sometimes prevent the negative impacts of those traditional coastal structures. Now, I just listed all of the good parts about natural and nature-based features, but there's also some challenges. First off, they're often using newer techniques that have less documentation, so people just aren't as familiar with how to build these. Also, nature is really complicated and really hard to predict. If you put a bunch of riprap on the coast, the point of the rocks is that they don't move, and so there is nothing to predict. With a natural and nature-based feature that's expected to change over time, it's a lot harder to predict exactly how it's going to evolve. Nature-based solutions are often more site-specific, so you can't just take a design from another place and copy it a bunch of other places. You have to really understand the system that you're working in. And like I said, the design's expected to change over time, which makes it also really difficult for people to wrap their heads around, and for permitting purposes, things like that. And lastly, natural and nature-based features are going to require maintenance, and that can often turn people off of them. I showed you pictures of what some natural and nature-based features can look like, but if you look at these pictures, you might think they don't look a lot like Oregon, and that's because they're not. So what do natural and nature-based features look like for Oregon? Well, one thing that we might consider is looking to our natural environments. So on the left, I have a picture of a naturally occurring composite beach. So this is a beach type that exists in Oregon. Typically, composite beaches have a really flat, sandy foreshore with a steep cobble berm at the back, and they are generally known to be overall a pretty stable beach type. And so we have started trying to replicate those. So on the right, there's a picture of a constructed dynamic revetment, and that's the language that I'll use from now on in the presentation. The natural version I'll call the composite beach, the engineered version I'll call a dynamic revetment. A dynamic revetment typically has a cross-section that looks something like what you see in the bottom right. So it's a mass of cobbles in an approximately trapezoidal shape that's placed on an otherwise sandy or sometimes beach with some cobbles that are already on it. And the profile of this dynamic revetment is expected to change over time. The rocks are expected to move, and I'll show you what that looks like. So this is how dynamic revetments work. The cobbles all have a tendency to move when they're impacted by waves, but overall the structure is coherent and stable. Typically, you can expect an increase in crest height as the waves are impacting the dynamic revetment. And because the cobbles have pores between them, the water is able to percolate down into the revetment, which helps to dissipate wave energy. And we actually have a lot of examples in the Pacific Northwest. And the most exciting thing about this slide, I think, is that I have had to add 3 new dynamic revetments to it since I started my PhD. So there's a lot of really active interest in these kinds of structures right now. So if you want to build a dynamic revetment, what parameters do you need? If you're an engineer and you're going to design a dynamic revetment, this figure shows a few things that you're probably going to have to consider. You're probably going to need to specify the crest elevation, or how high the top of the dynamic revetment is. You'll specify the toe elevation, how low the bottom of it is. You might have to specify the front slope or the crest width, and you're definitely going to have to specify the amount of rock that's going to go out on the beach. So how do you come up with these numbers? Where do you start? So we worked on a project to basically take all of the information that we have about how to get to this design, and we summarized it in one place. So we summarized design tools from academic literature, not only from dynamic revetments and composite beaches, but we also looked to areas of study like gravel beaches or even riprap. We also summarized the design process for constructed projects in the Pacific Northwest so that we could try and learn from those. And in the end, we proposed a design process, and this was actually published pretty recently. It's the audience of this paper and design process is intended to be engineers or people that are working on designing dynamic revetments, but it's also totally readable by an interested layperson. So if you're interested, I would suggest you check it out. Some main takeaways from the design process. I'm not going to go through this whole thing, but I wanted to point out a couple of things that stood out. We really tried to emphasize adaptive management, which is the idea that as your dynamic revetment changes, you can do adaptive maintenance to make sure that it's still functioning the way that it should, and that plan should kind of be developed while you're developing the initial design. We tried to address as many concerns about dynamic revetments as possible using a survey of practitioners to try and understand the things that people were worried about, to try and make sure that some checks about that were built into the design process. And another thing from this design process is that we really tried to acknowledge the knowledge gaps, because we really do not know everything about dynamic revetments. And so we tried to make this design process useful while acknowledging that we don't have all of the tools that we need. And in that vein, we really emphasize that engineers still need to use their best judgment to choose the best existing tools to design the dynamic revetment. A couple of other takeaways from this study is that dynamic revetments in the Pacific Northwest all had really different designs, but they were all successful to different extents, and different communities described success a little bit differently. Engineers typically used a mix of methods to design dynamic revetments. They used tools from other fields, they used lessons learned from existing dynamic revetment projects, and they used observations of nearby composite beaches. Another thing that I want to emphasize is that everybody really wants to know how dynamic revetments will perform, what will happen to it once you put it out on the beach. And so that suggests to me that we need to start making a shift from copying the successes of the past to being able to predict the future. And to be able to predict the future, we need more tools that are developed specifically for these dynamic revetment and composite beach environments. So in the end, we proposed a design process that can make use of the tools that we have while leaving room for better tools to be developed in the future. And you might guess where I'm leading here, because this is only the first part of my PhD. So the second part of my PhD is actually working on some of those tools to try and improve the knowledge that we have. The first thing I'll talk about today is improving our alongshore transport rate predictions on dynamic revetments. And the second thing I'll talk about is predicting the performance of dynamic revetments based on the cobble volume that's placed on the beach. So first, a definition. When I talk about alongshore transport, what I mean is I'm talking about rocks that are moving in the alongshore direction, so parallel to the waterline. And alongshore transport can sometimes mean sand, it can sometimes mean rock. Here, I'm only going to be talking about the rock that's being transported. And also, just for context, cross shore is the other direction, so things that are going towards the water and away from it. So why do we care about alongshore transport? First, in dynamic revetments, we know that alongshore losses can be pretty significant. We don't expect a lot of cross-shore losses, so the way that you're going to lose volume from your dynamic revetment is in the alongshore. And the volume loss is what's going to determine your maintenance schedule, how often you need to come back and put more rock on the beach to maintain the functioning of your dynamic revetment. And right now, we have no equations to predict the alongshore transport of cobbles on composite beaches. And that's kind of a surprising statement. Like, we do have a lot of equations for different kinds of transport, but I'm going to explain to you why composite beaches are kind of different than a lot of other beach types. So typically, when you're talking about alongshore transport, your longshore transport is going to be, the waves are going to be running up and down the beach. And your longshore transport is going to be happening like where those waves are running up. So at low tide, the longshore transport is going to be happening where those waves are breaking. At high tide, it's the same longshore transport is going to be happening higher up the beach. But on a composite beach where you're only concerned with the movement of the rock on the beach, at low tide, the rock isn't going to be moving at all. It isn't until it gets to high tide where the waves are actually going to be interacting with the cobbles that you're actually going to see any longshore transport. So that means that alongshore transport equations that work for composite beaches are going to have to account for this fact. And that has simply not been developed yet. So we did a field experiment to try and understand these systems a little bit better. We chose 3 sites, 2 natural composite beaches, that's Arch Cape and Falcon Cove in Oregon, and an engineered dynamic revetment, that's Westport up in Washington. We took 100 cobbles from each site, we drilled holes in them, and we installed RFID tags, which allow you to find the rocks with this funny looking antenna that I'm holding on the bottom left. So we replaced half of the cobbles in October, half of them in January, and over the course of the experiment, we went back about every 2 to 3 weeks to each site from October 2023 to March 2024 to look at transport over a winter season. And this is what our data looks like. So here you're looking at a satellite view of our 3 sites. The dots represent all of the places where we found cobbles. And the lines represent the cobble toe, so where the beach changes from rock to sand. And the colors, yellow is the earliest dates, purple is the later dates. So right off the bat, you can see that we had really significant northward transport at both Arch Cape and Falcon Cove. The transport at Falcon Cove was up to like 150 meters, which was really cool to find rocks that far away. In contrast, at Westport, we had nearly no cobble motion. And the major difference between these sites was that Westport had a cobble toe, a cobble toe that was at about 4 meters in elevation, where Arch Cape and Falcon Cove, the elevation of the cobble toe was more like 1 to 2 meters during the time period of this experiment. So that means that Arch Cape and Falcon Cove had way more interaction with the waves than Westport did. And that's why we think there was way more transport at Arch Cape and Falcon Cove. When we're dealing with this cobble data, we can kind of look at it in 2 ways. We can first look at the individual cobbles. So looking at how, for example, each cobble's mass affects how far or fast it's transported. And we can also look at things in terms of the cobble group. So in that analysis, what I've done is I've taken all of the cobbles and I've averaged them to 1 single representative cobble per site and then tracked that cobble over time. So I'm going to talk about the individual cobble analysis first, and we'll come back to the cobble group. So just to show you an example of the kind of analysis that we can do, we can look at the cobble mass. So on the y-axis of each of these plots, I've put all of the cobbles into groups based on how much they weigh, their mass. So on the left side are the lightest cobbles, on the right side are the heaviest cobbles. And on the y-axis, I have plotted their velocity, so how fast they're moving. And what I was expecting to see here was that the smallest cobbles always moved the farthest, that there was a trend that went from like the upper left to the bottom right for each of these, and that's not exactly what we're seeing. I've also plotted the mean of each of these bins. That's the open dark circle. So I'll step back for a second. I was expecting to see a trend in the mean transport for all of these bins. The mean transport would be higher for the smaller cobbles than the larger cobbles, and that's not really what we're seeing. We do see that a lot of the individual smaller cobbles travel way further and faster than the individual larger cobbles, but the mean doesn't really have that trend. And what we think is going on here is that the smallest cobbles are able to travel the fastest because they're the lightest. But they are also the smallest, which means they get stuck the most easily. So they're able to get stuck in between the cracks of larger cobbles. And so that means that on average, there's not a trend in the mass versus velocity. So that was an example of looking at the individual cobbles. Now I want to move on to talking about the cobble group. So again, here I've averaged all of the cobbles into one representative cobble to look at how that cobble group is moving in response to different wave conditions. We're going to look at a few plots, so I wanted to kind of orient you to what we're going to be looking at. So on these plots on the left side on the y-axis, we have the distance traveled by that representative cobble. And then on the x-axis on the bottom, we're going to have some parameter of interest, maybe wave height, wave period, that kind of thing. And then the plots will be comparing the parameter of interest to the distance traveled. And there's going to be a line through them that's going to show what the trend in the data is. And so if everything looked totally perfect, if there was a really good correlation between whatever parameter we were looking at and at the distance traveled, this is what our data would look like. All of the points would fall neatly along the line, and the R-squared value, which is basically just telling you how good the fit is, would be 1. That's the best you can do. So moving on to look at some actual data. So here I have 4 plots. On the top left, I have plotted the distance traveled versus the average wave height. The top right is the distance traveled versus the average wave period. Bottom left is the distance traveled versus the average wave direction. And on the bottom right is the cumulative wave power, which is a measurement of the wave height and wave period accumulated over time versus the distance traveled. And you can see that out of all of them, there's one that looks the most similar to the hopeful perfect fit that I showed you in the last slide. And that is this cumulative wave power that's on the bottom right. That has an R-squared value of 0.63, which is a pretty good fit. I was very happy when I finally saw that plot come up. So another thing that I wanted to explore is what happens with that calculation when you include all of the data versus when you only include the data in which the waves were interacting with the cobble berm. So here on the right, I'm showing what this plot looks like if I include all of the data, if I use it all to calculate the cumulative wave power over the time period that we're interested in. And it does okay. The R-squared is 0.44. You can kind of see a trend. But that fit gets a lot better when we throw out all of the data that took place when the waves weren't interacting with the berm. So we can see again, like I explained, that accounting for the fact that the waves are sometimes not interacting with the berm ends up being really important in being able to predict how far these cobbles are being transported. So the next thing that I'm working on now that we've figured out what one of our more important parameters is my goal is to develop an equation that engineers are going to be able to use when they're designing their dynamic revetments to predict how much longshore transport they're going to see. And so other equations that have been developed for gravel beaches or sand beaches, they're typically of this form. So they have a wave height term, a wave period term, something to do with the slope of the beach, the size of the grains, and the wave angle. So here our plan is to substitute cumulative wave power in for both this wave height and wave period terms. And for the rest of the terms, we're still working out which ones are important and which ones need to be included in the final equation. But in general, this is where we're headed. So some takeaways for this alongshore transport piece. We observed northward transport of cobbles up to 150 meters during a single winter season, which was very cool. On average, cobble mass doesn't seem to impact the transport distance that cobbles are being transported. We found that cumulative wave power is the best predictor of transport rate, and that prediction gets better if we only consider times in which the waves were interacting with the berm. And finally, we're working on an equation that will be able to help predict the longshore transport rate. So I told you I had two tools to talk about. I've covered the first one, alongshore transport. Now I'm going to move on and switch gears to talking about cobble volume. So cobble volume has actually been suggested to be the only parameter that matters for dynamic revetments. And the reasoning for this is that because the revetment is dynamic, it's expected to change shape. So that means that the front slope is not going to be constant. The crest elevation and the crest width, they're not going to be constant. The only thing that's going to relatively stay the same is the cobble volume. But this idea is based on a really cool lab study that didn't consider any sand. So their lab study was done only with rocks on a concrete slope. And it was also based on wave conditions in Lake Michigan, which is useful, but obviously very different than what we get on the outer coast here. So we did our own lab experiment. The objective of the experiment was to understand how cobble volume is related to dynamic revetment performance. We used a 1 to 12 laboratory experiment, and we were in the Army Corps of Engineers flume in Vicksburg, Mississippi. We had a glass wall, so we were able to see what was happening inside of the berm. And importantly, we used sand. So we wanted to test different volumes of cobble, and we also tested different cobble shapes and different amounts of initial sand infilling into the revetment. I'm only going to focus on the different volumes of cobble for this talk. And also not going to go too much into the details about this, but I just want you all to know that these configurations are based off of the general range of cobble volumes that are in Oregon and Washington projects, and our wave conditions also come from what we see on the Oregon and Washington coast. So we tested 4 volumes. We're going with the t-shirt sizes for now. So we have an extra small, a small, a medium, and a large volume. And I'm going to show you how some of those tests went. So some main takeaways, the medium and the large volumes both succeeded under the storm conditions that we tested them under. And what success looked like in this experiment was there was limited overtopping of waves onto the back of the beach. There was limited infilling of sand into the revetment. There were lots of mobile rocks, so rocks were able to do a lot of moving around. And there was an overall increase in crest height of the revetment, and I'll show you what that looks like. So here you can see that the cobbles are pretty mobile. They are forming a crest up at the top. The crest elevation is increasing, and there's a little bit of infilling into the revetment, but not a ton. So, oh, and it's also a little bit difficult to see here because you can't see the individual waves, but there was not a ton of overtopping over this crest onto the back of the beach. In contrast, both the small and the extra small volumes failed under storm conditions. And what failure looked like here was a lot of infilling that completely filled in the dynamic revetment. That resulted in very few mobile rocks. So there weren't enough rocks to move around and be able to form a higher crest. So overall, the crest stayed about the same and the whole cobble profile kind of flattened out. And there was lots of overtopping, which took any rocks that were mobile and washed them to the back of the beach where they weren't useful anymore. And so I'll show you what that failure looked like. This was our small revetment. So you can see a lot of infilling right at the beginning, hardly any rocks that are able to move around and dissipate wave energy and absorb some of that water. the waves are washing over any loose rocks that do form into the back of the beach over here on the left, where they're no longer able to be used for protection. So I talked to you earlier about the study that had suggested that volume was the only parameter that mattered. And they provided an equation to be able to calculate what they called the critical volume. So their theory was that if you, for any dynamic revetment geometry, if your volume was lower than the critical volume, your revetment would fail. If it was higher than the critical volume, your revetment would succeed. So I've highlighted in red the two tests. I did this calculation for all of our revetments, and that's the critical volume that was given by that equation. That's in that last column over here. So the boxes that are highlighted in red are the places where the critical volume is greater than the revetment volume that we tested. So that's showing that those two revetments are expected to fail. Then I've highlighted in red the two revetments that actually failed. So we can see that there's a little bit of a discrepancy here. Then I've also highlighted in green the revetments that succeeded. So what this tells us is that the best available equation that we have right now is really over-predicting the volume that's needed for a safe revetment. And this discrepancy gets larger with increasing depth of the water at the toe of the revetment. So that's why there's such a discrepancy in this large revetment on the bottom row, because the water depth was greatest at the toe for that revetment. And anecdotally, that revetment definitely looked the most stable. So we can tell that there's something that's not quite right here with the way that these critical volumes are being predicted. So that's what I've done so far. For ongoing work, I've talked a lot qualitatively about the performance of these dynamic revetments, showing you videos of the crest height increasing and telling you that overtopping is happening. But I'm a scientist, so I have to quantify this. So ongoing work is to work on quantifying the performance. So looking at the overtopping rate, looking at how high the water is running up onto the revetment, and looking at how much the crest height increases over the course of a test. Those are just examples. There may be other things that also get included in this. Then once those things are calculated, we can explore the relationship between the volume and those quantified performance indicators. And our goal with this is to be able to provide guidance on what a safe volume for dynamic revetments might be. So some main takeaways. We were able to qualitatively characterize dynamic revetment success and failure through our lab experiment. And we also were able to show that the best existing equation is over-predicting the critical volume needed for a dynamic revetment. So in the future, we're moving towards providing better guidance on what this critical volume might be for dynamic revetments. So to kind of recap where we've come in this talk, we started off by proposing a design process that can make use of currently existing tools and tools that can be developed further into the future. Then we started working on the tools. We did a field experiment to improve predictions of alongshore transport. And we did a lab experiment to improve predictions of dynamic revetment performance based on cobble volume. And both of those things are able to be plugged back into that design process that we initially proposed, so that engineers are able to use better and better tools to be able to predict how dynamic revetments will perform. And so this can go differently for different types of structures, but for us, we're really hoping that this is a way that we can continue supporting engineers through our science as they continue to design and construct these cool structures. Before I leave you, I want to talk about some other work that's going on at Oregon State, because I am not the only one doing dynamic revetments here. We have a master's student, Louisa Wise, who is looking at the ecology of dynamic revetments. We have a master's student who just graduated, Colin Arnowell, who looked at alongshore and cross-shore sorting of grains. We had a postdoc recently turned assistant professor at Utrecht University, Christa van IJsendorn, who looked into aeolian sediment transport, which is wind-driven sediment transport onto dynamic revetments, which we think might influence the infilling of sand into dynamic revetments. And lastly, we have a PhD student, Andrew Schultz, who is looking at run-up on dynamic revetments using lots of camera imagery that we collected during the field campaign where I was running around the beach looking for rocks. And with that, thank you. And I'll leave the QR codes for the papers that have been published on this recently, so that if anybody is interested, they can go check them out. They're both open access. And so if you want to read them, you totally can. Thank you.
Thanks so much, Haley. Are you willing to take some questions?
Absolutely.
All right. Feel free, attendees, to put them in the chat, or you could raise your hand and I could unmute you. I guess while we wait for some questions to come through from our audience, I have one. I
Yeah,
was
for sure.
wondering, since you created the guidebook on organ control practices here in Oregon, and you've done all this research, all this wonderful research, I was just wondering where you see dynamic cobble berm revetments kind of fit in terms of like the suite or the menu of erosion control practices.
Yeah, that's a good question. I think what we're continuing to learn is that it's all nuanced, right? I don't think that dynamic revetments are appropriate for every situation. I don't think they're going to be particularly good for a single home because of the alongshore transport problem. There's just not a lot of volume where we'd be worried about it like spreading out too fast. But places where they can work really well are in front of condo complexes. This is Westport up in Washington, where the condo complex got together to all pay for this dynamic revetment, and it's been really, really successful there. Dynamic revetments are also good options, I think, for maybe potentially like ODOT or WashDOT projects, where it's a longer area of shoreline that needs protecting with a little bit of a heavier, shoreline protection structure. It also has worked really well up in North Cove, where it was like an entire community that came together to protect a stretch of coastline. So I think that's where these kind of fit in on kind of the like condo complex neighborhood level. I think in those cases, they're a really, really good option and should definitely be tried at least, because in some cases they're cheaper than riprap.
That's awesome. Thanks so much. And that helped address one question that Rebecca asked in the chat, asking, is
Yeah.
this a cost-effective solution to erosion?
Yeah, I think so. I am definitely I'm on the science side, so I'm a little bit removed from the like cost and construction. But from what I've read, well, first, the cost can vary super widely. So, for example, at North Cove, up in Washington, that's a community level dynamic revetment intervention, and they have paid for it with grants. They have paid for it with bake sales and community fundraisers. They've gotten rocks. For example, there was a bigger project that was built, the Empire Spit project, and they had to build a haul road made out of cobble-sized material for that. And the North Cove community was able to get some of that haul road material and use it for their dynamic revetment. So you can go really, really thrifty and a little bit cheaper. Then there's also Army Corps dynamic revetments that involve like building a dune behind the dynamic revetment, making it really, really big. I think that project was using that critical volume concept that I talked about. So it's a big revetment. So depending on what the purpose is, it can kind of range from pretty cheap, relatively speaking, to like a very expensive project. It was possible for the whole condo complex to come together and pay for this one. I think in total it cost them about $1 million. So it's comparable or cheaper than riprap is kind of what I understand. And can obviously, the cost can vary based on like what your community wants.
Great. Yeah, thanks. That makes sense. I had a question involving the other graduate student who's researching ecology of dynamical
Yes.
revetments, and then Rebecca, thinking on the same train of thought, she said, "What impact does this have on intertidal sea life?"
Yeah, so that's a great question, and one that we realize that this is a really big hole in our understanding of these structures, and one that we're actively trying to fill. So Louisa, the master's student that's working with us, is mostly focused on plants. She's co-advised with Sally Hacker and Megan Wengrove. So she's combining the dynamic revetments part of things and the plant part of things. So at this point, we don't know yet what impacts it can have on intertidal critters. But two pieces of information. First off, lab studies have shown overall in several different lab studies that the amount of cobbles that we lose to offshore is not a super big amount. We're expecting that most of the cobbles, when you build a dynamic revetment, that most of the cobbles are going to stay as part of the structure because the waves have a tendency to want to push them up. So for that reason, we're hoping that they don't have a lot of negative impact on intertidal critters. On the other hand, something that we've heard anecdotally at the South Jetty, where a dynamic revetment has been constructed, I've heard through others that some of the clammers there have been starting to run into rocks when they put their clam guns in the water. And so that's obviously not ideal for the clammers. So we definitely need to understand more about the ecological impact of these, and that's something that we recognize is really important and are actively working on.
I have a question. Sorry.
Yeah.
Um, so you talked a little bit about like North Spit community level or
Mm-hmm.
organization around creating a cobble berm. Um, and then the condos. Do you know of any examples in Oregon of like multiple landowners across multiple lots coming together so that they have enough space for a cobble revetment to work?
No, we don't have an example of this in Oregon. And I wonder sometimes if that's because of the permitting environment, if there's places in that like some people are eligible for riprap and some people aren't. And so it's maybe a little bit harder to get a whole group of houses on board. I'm just speculating. I have no idea if that's actually the case or not. But Washington doesn't have they have different restrictions. So I think I wonder if maybe it's been possible or easier for communities to come together up there. But as of now, we don't have any examples of this in Oregon.
I guess a follow-up question to
Yeah,
that. Because we see places like Salishan where,
yeah.
most of the lots are armored. What would it be possible to, in a place like that, like remove the riprap and replace it with something like a cobbler revetment because you have like miles of space to work
Hmm.
with?
I mean, that sounds expensive. But if the riprap needs to be replaced anyways, I personally think that could totally be a possibility. Um, but I'll caveat that. One of the things that we saw when we did our survey for the state of the practice paper to try and understand the way that people were thinking about dynamic revetments and the concerns that people had, one of the categories that we kind of developed for categorizing the survey responses were that people were really concerned about what we called changing the character of the beach. So turning, like, I've talked about how these composite beaches exist naturally in Oregon, but they're not everywhere. So it's not nothing to change your beach from a completely sandy beach to a composite beach. And last I talked to Oregon parks, um, there's reasons that they might have to like not approve dynamic revetments for that reason because they are like significantly altering the beach. I think there's like pros and cons to that, and it's something that communities have to kind of decide and decide whether they're okay with like losing their beach to riprap or changing it from a sandy beach to a composite beach. Just pros and cons there. And that might apply to some place like Salishan.
Thank you. Yeah, that makes sense.
Well, if there are no more questions, I'm happy to wrap this up early. Maybe we'll give 30 more seconds for people to chime in case they have last minute questions. But Haley, thanks so much for presenting with us today. I learned a lot.
Thank you for having me.
I am going to put a link in the chat to all of the events that I mentioned at the top. So if one of those speaks to you, you can find more information and sign up links at that link, oregon.surfrider.org, OBF events.
Sounds good. I'll also
Oh,
send
sorry.
a
Okay,
follow-up
now it's in the
email
chat.
with all the links as well. Thanks so much for joining, everyone. Have a good rest of the evening. And Haley, thanks again.
Thank you.
Yeah, thanks, Haley. Good night, everybody.